Welcome to Spirit of Math. It is a well-known fact that if you take a circle of perimeter P and of radius R, and if you take the ratio of P over the diameter to R, you get a constant known as pi. Pi is a well-known constant since the Pharaoh, and we know an approximation of this constant for the more famous one is 3.14. And for centuries, mathematicians wondered whether P is a rational number, which means that P can be written as a fraction of A over B, where A and B are integer. And the first rigorous proof of actually the irrationality of P, this means that this proof shows that P is irrational. It cannot be written as the quotient of two integers. This proof was given in 1768 by Lambert, a German mathematician. And Lambert showed that if you take a rational or non-zero rational number, then its tangent is irrational. And by contrapositive, since the tangent of pi over 4 is equal to 1, is rational, then pi over 4 cannot be rational, and pi cannot be rational. And Lambert actually considered the continued fraction of tangent x. He showed that tangent x can have this continued fraction, and he showed that if you take a rational number, then this continued fraction cannot simplify or terminate unless x is equal to 0. So if x is rational, then tangent x is irrational. And since this proof, many other proofs appeared, often simple and more elegant, and the most famous one is the proof of Van Niven in 1947. This Van Niven, in a short paper, gave an elementary, clear demonstration of the irrationality of pi. In this video, I will give you the Van Niven proof of more stronger result, namely pi square is irrational. So if we show that pi square is irrational, then pi is irrational. We will see that the Van Niven's proof is simple because it involves some elementary tools in calculus, but it is, in my opinion, still a mysterious one. We will see that it's not easy to have an intuition or a naturality of this proof. So let's go and give the idea of the proof. The idea of Niven's proof is as follows. First, the proof is by contradiction, as usual. So we suppose that pi square 2 is equal to A over B, where A and B are integer. And Niven consider this sequence of polynomial function. They are polynomial function of degree 2n. And the core of the proof is the following. Even consider this integral pi, the integral from 0 to 1 a power n fnx sine pi x dx, where a is this integer, fn is this function, and what Niven show, it shows first that this integral are actually positive. They converge to 0 when n goes to infinity, and more importantly, he shows that this integral are actually integer. It's the difficult part of the proof. And now if you have a sequence of integer which goes to 0, this is impossible of positive integer, because we have this result. If you have a sequence of integer which converges to O limit L, then the sequence must be constant. The fact that it's integer plays an important role in this situation. This assertion is easy to show. So the integer are positive, it converges to 0, and it is the contradiction. Now, why the integer are positive? It's easy to show, because this function is positive, continuous, and so the integer cannot be equal to 0. We will see, we will express the reason clearly. Now, why this converge to 0? Because this function in the interval 0, 1 is less or equal to 1 over factorial n. Sinus px on between 0 and 1 is less or equal to 1. So the capital N is less or equal to pi a n over factorial, and we will show that this converge to 0. So first we will show this fact and this fact, and the more difficult part is this part, and I will show it later. So let's so we have this integral, and fn is this polynomial, and we have this well-known result in analysis. If you have a continuous positive function on a closed interval AB, and the integral is equal to 0, so the function must be constant equal to 0. So this, if you use this the contrapositive of this this implication to this function, we get that capital N is positive. Now this function is less or equal to 1 over factorial n, so we get this result. So this part is so easy. Now we will show that this sequence converges to 0, and we deduce that capital N converge to 0. Indeed, we will use the Stirling formula for factorial n. This is a well-known formula, and now by using this formula we get that this limit is equal to this one, and this goes to 0 when n goes to infinity. Let's show that this one goes also to 0 by writing this as an exponential. So here we get that this is equal exponential n ln a minus ln. This quantity goes to minus infinity, n goes to 1 plus infinity, so the product goes to minus infinity. Exponential minus infinity is 0, and we are down. So we have shown that this limit is equal to 0, and we deduce that the limit of capital N is equal to 0. Now we tackle the difficult part. Let's start by giving the fundamental property of this polynomial function, which will be used later. So this is a polynomial which can be written as a sum for k from 1n to 2n, and the ck are integer 1 over factorial n, and this double inequality is easy to see because x is between 0 and 1, and 1 minus x is also between 0 and 1, so we get easily this one. And the more important property is that the successive derivative of fn in 0 and 1 are all integer. It is the more important part, and I think that it is the reason why Niven introduced this polynomial function. So the proof of this lemma is very easy. If you compute the k derivative of fn at 0, you get 0 if k is not in n to n, because here we start at n and we finish at 2n, and if k is between n and 2n, the k derivative is factorial k ck over factorial n. Now k is greater than n, so factorial k over n is an integer, and ck is an integer, and we are down. For the derivative on 1, we have this formula which gives us the derivative of n on 1 in function of the derivative from 0. And we have shown this important property. So this polynomial function satisfies this property. Now let's tackle the difficult part of the problem. So far we suppose that pi square is equal to a over b. We considered this sequence of polynomial. We have shown that this integral is positive and goes to 0 when n goes to infinity. and we just shown that we have this result. So now we will show that capital N is actually an integer, and it is the mysterious part. So what Niven does is he gave an antiderivative of this function, and in not usual way. In my opinion, in a mysterious. So Niven computed an antiderivative of this function to compute this integral and to show that it is actually an integer. So I will give you the method used by Niven to derive the antiderivative of this function. So first, Niven considered this function, capital Fx, given in function of the derivative of Fn, where we see here we have pi over 2n minus dk. And the first remark is that the coefficient b power n pi power 2n minus 2k is actually an integer, since p square is equal a over b, and pi 2 n minus k is equal to a n minus k b n minus k, and we get this. So these coefficients are actually integer, and we deduce the important fact that f0 and f1 is an integer. It can be negative because we have this sign here. And now what we will do, we will compute the second derivative of this function to get a formula which will leads to the antiderivative of this function. So let's start. We start by computing the derivative. It's used by computing the derivative of this function. So we take 2k plus 1 here. And now the second derivative is also easy, and we will here replace k plus 1 by k and get this formula. So if we replace k plus 1 by k, we get here 2k, we get k will begin k minus 1, and we get this formula, and we start here, we start from 0 to n. Here we will start from 1 to n plus 1. And now we have here pi square, which factor here, and we have minus k minus 1, so we will have minus here, and we get this formula. So here it's look like f capital X, and we need the term for k equal to 0, and we have a term for n plus 1, but we have seen that fn is a polynomial of degree 2n, so the 2k plus 2 derivative is equal to 0, and we will get this formula. So we have added and this term to get this one. in this form because here we need k equal to 0. So we have this formula. So we have shown that the second derivative of fx is equal to this. Now, so we have, we summarize, we have this function, we have this property, and we have shown this. And now we will get the antiderivative, the part. So Niven considered this function gx equal f prime x sine pi x minus pi fx cos pi x, and in fact its derivative is actually the antiderivative we are looking for up to a constant. So we compute the derivative of this function. So we here it's a product, so we here f the second derivative for a sine pi x plus the derivative of sine is pi cosine pi x minus the derivative cosine pi x, and here we get the derivative of cosine, it's minus pi sine pi x, and we get this formula. These two terms cancel, and we replace here f square by this term, and now this term and this one will cancel, and we get what we are looking for. So we have this function, and actually we have shown that the derivative of xi is equal pi square, because this quantity is equal to pn a square a n over pn, and we get this formula. And now we are done, because we have found the antiderivative of a n f n x sine pi x, and we can conclude now. We have our integral, and this is equal 1 over pi the derivative of x, and we use the fundamental theorem of calculus, and we get this result. Now g1 is equal to cos pi minus 1 f1 pi, and we get this formula, and we have shown that this is an integer. So we have done, because now we have shown that this is positive, so we get what we need, and we have done. Okay, and now so to support the channel, please like, subscribe and share, and thank you.